Thanks for coming back. So today we'll sketch the ideas of the proof of sticky Kakeya theorem. The theorem was like for any sticky set of delta tubes, for delta eta dense shading, we have the union of those tubes or shading has volume greater or equal than delta to epsilon times the number of tubes times the volume of one tube. And this means that the tubes are essentially disjoint. And last time we showed some idea of how to prove a claim, saying that with the assumption that the number of tubes is roughly delta to the minus 2. And so this is our sticky Kakeya theorem, but we said that it's okay to add this additional assumption. And the reduction to this case, I sketched some randomizing argument and also like how the maximal density holds after decomposing the tubes into like thick tube and thin tube in thick tube. So all I want to say is that this reducing to this case is in section 7 of streamlined proof of Kakeya set conjecture in R3. This is I just uploaded this early morning on my website, so you could see it. It's because the reduction to this case is like self-contained, is independent from the rest. So I didn't. I just sketched the idea, didn't go into details. But for details, you could check section 7. Okay. So yesterday we also said that we are going to induct on this statement. Let's say kappa s beta. For any epsilon greater than 0, there exists eta for any eta between the following holds. Let T be delta eta sticky. So I should say this just means that the maximal density of this is less than delta to the minus eta for any row of the form delta to the eta j. So if this is a delta to the eta sticky set of delta tubes, and similarly y is delta to the eta shading, then mu, and let me just shading density greater than this, then the multiplicity is bounded by delta to the minus beta minus epsilon. We are going to show that this is the statement. We are going to show the following. Kappa sticky beta implies kappa sticky beta minus nu for some nu greater than 0. Okay. So this is the inductive statement we want to prove. Yesterday we also draw the following picture. So recall that the multiplicity is roughly the number of tubes through a typical point. And here, let's say this this is rho, and let's say the point in the middle is a typical point x. So this is x. We know that the tubes the tubes inside a row tube intersect into some segment grains of side length. Of length delta over rho. So those are grains G. Last time we said that we have the following. Where this blackboard G is just the set of grains. So by pigeonholing, this holds in general. And this is the multiplicity decomposition that appears here, and we are also going to study to use it heavily in the general case. But usually there is another more obvious bound. That is, this is less than the multiplicity of thin tubes inside a thick tube. So in this picture, it's just how many thin tubes here passing through this grain, times the multiplicity of T rho Y. So how do I define the shading on T rho? Let's be a row tube. The shading is just, let's say, a row neighborhood of the union of thin tubes inside it. Okay. So that is the definition. We are going to start with the following. Suppose suppose T is sticky and has cardinality roughly delta to the minus 2. Notice that this assumption together implies the following. Implies all the T rho is sticky, and the cardinality of T rho is roughly rho to the minus 2, up to some powers of eta, delta to eta, and also T rho is sticky. So sticky probably with some other parameter, but still sufficiently small. And then T rho is roughly. So again, as last time we said that this is the reason why sticky sets is very good to do induction. Now, so what I'm going to describe in the maybe next 10 minutes or so works very generally for any sticky sets in other problems as well. So also we are going to assume that T is extremal in the following sense. Extremal means that the multiplicity, so I should say that also this Ty is extremal. The multiplicity is greater or equal than delta to the minus beta plus nu. This nu is the improvement we want to find, and assume that we cannot do this improvement. It means that there must exist a set of tubes such that the multiplicity is bigger than what it predicts. Okay, so this is what we are going to assume, that is extremal. Then let's see the key observation for the sticky case, not only for the Kakeya problem but also for other problems, is the following. So this extremal example will produce the extremal set of T rho and thin tubes inside thick tube. And this gives us a lot of structure. So how to do that is fairly easy. in this, because we just need to compare the inequalities. So this is, we know that it's greater or equal than delta to the minus beta plus nu. By induction, we can do induction because we said that T rho is sticky, and also the T rhos are also satisfies the hypothesis with rho in place of delta. So here by induction, this is less or equal than rho to the delta over rho, because this rescales to I will use T upper T rho as rescaling T rho to the unit tube. So this becomes a set of delta over rho tubes. So then we can apply induction with delta over rho in place of delta. So this is less or equal than this minus beta minus epsilon. And this is less or equal than rho to the minus beta minus epsilon. And then if we compare them, this altogether is less or equal than delta to the minus beta to minus epsilon. And it should be also greater than delta to the minus beta plus nu. When nu is very small, this means that all the inequalities has to be essential equality. So the key observation is that okay, let me just write here. Just by induction and also by the hypothesis that this is extremal, it implies the following. It implies that mu T rho is roughly minus beta plus O nu. I'm going to take, let's say, take epsilon less than nu, because epsilon can be arbitrarily small. So I will just use nu to bound epsilon. That's why I'm omitting the epsilon here. We know that mu T rho, y is roughly rho to the minus beta plus I should probably say delta to the O nu, just to be safe. But usually we consider, let's say, rho is greater or equal than some scale this is not too far away from. It is still very small compared to delta over rho. Okay, so we have this. They have to be, like here it says that they also have to be essentially extremal, and this is the first observation. And the second observation is to improve this bound, it suffices that we improve one of them. Suffices to show let's say for some very big C, that this C will dominate those constants here. This should be, less or equal. And then the third one, that is the most important observation, is as follows. If X is if a delta ball X is contained in T rho intersect the union of tubes, then there exists a T inside T rho such that X is contained in its shading. So this holds with probability of delta to the O nu So I say with probability, what I mean is like after some pigeonholing. So I'm doing a little bit hand wavy here. Okay, so how does the last line is true? Let's pretend all those epsilons are new, they don't exist. Then what does it mean is that, so let's look at this picture. So if we pretend all the small parameters don't exist, then we know that the number of tubes, the multiplicity of t, of blackboard t, the number of tubes through this point, is roughly delta to the minus beta. And also we know that the number of thin tubes inside this yellow thick tube through this point is roughly delta over rho to the minus beta. So this means that the number of those segment grains through each point is roughly rho to the minus beta. So we have a rho to the minus beta many segments passing through it, and each segment will associate with some thick tube. We also know that the number of thick tube passing through it should be at most rho to the minus beta. So in particular, this means that if there is a thick tube passing through this point, then there must be a segment passing through this point. So that's the point C, and this is the most important part for the sticky case. We also have very similar observation for sticky case of other problems, and this number C. And at this point is very general, and then starting from here, we are going to specialize for sticky Kakeya sets. And if you feel that the picture after this point is too complicated, you can relax, and because it's going to be black boxed. Okay, is everything until this point clear? So we are going to use this property C to deduce a structure of sticky Kakeya set. So from now on, we specialize to sticky Kakeya sets. So claim we are going to pick rho to be delta to the 1/2. This has the advantage that delta to the 1/2 just equals to delta over rho. Then what I'm going to do next, is just highlighting the ideas. I'm not going to go into too many details. So we said that for a typical B rho inside the shading, the Kakeya set inside intersecting this B rho is roughly a union of slabs. Let's give this collection a name. Well, this is a set of parallel delta times rho slabs. Okay, so when I say approximately equal, I mean the following. It's include in this and also as intersect, it is roughly 4. So that is what I mean by roughly the union of S. How to prove it? So the picture really is, let's say, this is a typical. So sometimes I would use B rho to both denote a ball or a cube. So because for cube it's easier to draw the slabs. So for this is a typical B rho, and then inside it So, I don't know if so it's going to be a union of, I guess my picture is messier than I thought. Anyway, so it's the union of parallel slabs. And so to prove this claim, we just use this C. And how do we do it? So proof sketch. So the first one is bilinear reduction, meaning that we can assume that for a typical B row, for a typical pair T1, T2 inside. So recall that this is the set of tubes passing through X. We know that the angle T1 and T2, let's say, is roughly R. I claim that this should be greater or equal than delta to the nu over beta. Just means that a typical pair of tubes through one point should have an angle large. So we should view this as roughly 1 because nu is a very small number. And for otherwise, we have the multiplicity is bounded by sup of TR, multiplicity inside. And by induction, this is less than delta to the minus beta plus nu. Induction. It just says that if a typical angle is small, then we might as well, we could show that the union of thin tubes inside this R tube for different R tube, they are essentially disjoint. And so we could assume this big angle separation. Otherwise, we are done. Is it clear to this point? Okay. So this is the first argument, the first step. And the second step is where we could, so let S be equals to the span of T1 and T2. So now we fixed T1, T2 passing through this point with a large angle. I use this, okay, let's say just angle large. We fix a pair T1 and T2 intersected point, and S to be the, like T1, T2, we should think they are like two lines, and then they span a tube plane. And then since T has radius delta, so this has a delta neighborhood, intersect this ball of radius rho centered at X. Then we claim that S intersect the union of tubes is greater than, so means that we have the correct density. It's very dense, and this is the step that we use C. And so, okay. And how to do it? We fix, let's say, T1 and T2, and this is our x. We are going to take row neighborhood, and since row we take it equal to delta to the 1/2. Then from this point C, we know the follows. So again, by our pigeonholing, we know that T2 lies in a thick tube. Let's say on this T row. So T2, we take the row neighborhood of T2. This becomes a row tube. And then this X is in our Kakeya set. So this is a delta ball X contained in T row intersecting the Kakeya set. Then it says that so for now, I didn't do anything, then there exists a T2 intersecting X. We know it already. But the point is that this holds also for other points in the shading. So there is this T1 going through X. So there are so we might assume the shading of T1 intersect B row is roughly greater than T1 intersect B row. Let's assume the shading in this part of segment is relatively dense. Then we apply the same C to other points Y. So for this point Y, we apply number C. We know that there will exist some other segment, some other tube inside T row passing through Y. That is number C there. And also for this point, for all the Y's that are on this segment, there will be some other tube inside T row passing through Y, and pointing in and contained in T row. So it's pointing relatively in the direction of T2. So the existence of those thin tubes inside T row passing through all the points in this segment. So maybe I should draw the color, a different color here. Is a consequence of C. And now the next observation is that since rho is delta to the 1/2, the union of those segments intersecting B rho lies in a slab, because this is delta to the 1/2, and then this, let's just call this T. We know that the angle difference between T and T2 is less than rho. So this means that inside this B rho, they should look like roughly parallel, because this has a length delta to the 1/2 and thickness and delta. So this is less or equal than delta over rho. In fact, they are all equal. So what do we see is we see a segment, let's say this yellow segment of length delta to the 1/2, and then through each point, so this yellow segment is in R3, through each point of the yellow segment, we have this red segment of length delta to the 1, also delta to the 1/2, and thickness delta. And through each point, we have another red segment, and they are all parallel because their angle difference is like absorbed by the error. So they're all parallel. And then this becomes a slab. So this altogether is our slab S. Okay. And since each of those segments, again, after a lot of pigeonholing, we can assume that it's rather dense. So that's why S has large density. And so this is this S is called the local grains. So I should give them a name. This S is called local grains. So we are not done yet. We have successfully found one S, starting from a point X and a pair of tubes passing through X. So maybe let me just say why we need the angle to be approximately like large, is because otherwise we want this red segment to have large angle with this yellow segment. Otherwise it's pointing like it does not span a slab. Okay, so we are not done yet. We have found one local grain S. We are going to, here there is one thing that's important, is that this decomposition, all the grains are parallel. How do we guarantee that? So that is, we are going to use number 2 again. So the third point is that, the third point is to prove a coplanar. And this is also the graininess, or planiness, I think, in the property that's in cat slab and tau. So this just means that for a typical T3 in Tyx, I should say the set of T row Y containing X. Let me just T1 wedge T2 wedge T row is less than rho 1 minus O nu. Why this is true is because so here we have I'm drawing this too fat, but let me draw the picture here. Where is my color? So here we have 2 tubes, T1 and T2, and this is our X. If there is another T row intersecting it, by C again, since T row intersect contains 0 X, and X is a point in the Kakeya set, there must exist a T3 containing X. This is a T3. And suppose T3 is not coplanar with T1 and T2 up to this error. So coplanar in a rough sense, in the sense of row. Then we could repeat this argument again and show that here we have a slab. If there is another direction that's not coplanar, we could, if like going the third direction that's not that's sort of transverse to the slab, then we also have, let me just redraw the picture. Let's say this is our slab. If there is a third direction going up, not up, like even slightly like not coplanar, then we know that by the same argument C, for each point in this direction, there we can find the thin tubes intersecting it. So this means that the slab, it should fill out a 3-dimensional rectangular box of the thickness, let's say, much greater than delta. And then here we are done because we know that the Kakeya set locally fill out a dense ball. So this is and we are done by induction. because T row, like T, let's say this is tau, because T tau also satisfies the hypothesis, then if we know that it's very dense inside, then we are done. So that is why we can deduce that this is coplanar. So all this, you can see that this is the power of a number C. C is like saying that everything is very rigid, and from this rigid property, you all of a sudden have all this nice structure of the Kakeya set. So let me just draw the structure of the Kakeya set. Also, this whole argument, I learned it in Tao's blog. I think he wrote it very well. If you are not happy with my explanation, you can read his blog post. Okay, so what do we learn from this claim? Since for the sticky Kakeya set problem, the part that we use the property C here is just to use to prove this claim, so I erase that property. And what do we know about the claim? It says the follows. Let's say this is a delta to the 1/2 tube, and then we know that at each delta to the 1/2 ball, the Kakeya set looks like a union of parallel slabs. And then at different delta to 1/2 ball, the slab might pointing in different directions. Let me just draw another one here. So they might pointing in different directions. Let's say this direction. But they have to, the slabs could not point in this way because the slab has to be parallel to the direction of this T row. So if T row is vertical, the slabs should always be vertical, but can rotate. Yeah. Okay. So that is this red set, those union of parallel planks, is precisely the structure of the Kakeya set. So let me just explain the claim. So this is what we call the, let's say, claim prime 2. This is that's 1. Local grain decomposition. It says that union of T intersecting B row. So for any B row inside the shading is roughly and this is roughly the union of slabs. Okay. Yeah, and I think this is important structure, like finding the structure of the sticky Kakeya set part. So are there any questions? Okay. Okay. So recall that this T, let me use the rescaling of T tubes contained in T row is sticky and extremal. So what's going to happen is that, and what are we going to do is we are going to, so the goal is to show the multiplicity of which is the multiplicity of the corresponding shading, rescaling shading, is less or equal than delta to the nu. So this is our goal. What are we going to do is that since this is sticky, okay, first of all, let me first draw what this set is. This is a rescaling of this picture, but then what happens after rescaling? So it rescales to a unit tube, and then each of those row ball is going to be a horizontal slice. So this, let's say, is row. And then each of those slab becomes so previously it also has some thickness. So it becomes a horizontal tube. Here it has a length 1, because this has length row, and then we stretch row to 1. And because they are parallel, so we get a set of parallel horizontal tubes. Okay. So this is what is. Again, there are some other pictures that other horizontal slices that I didn't draw. So this is a rescaled Kakeya set. Now we know that this rescaled extremal Kakeya set at scale. So this is a set of Kakeya set at scale row, a sticky Kakeya set at scale row. Now is a union of parallel slabs, parallel horizontal tubes, because the slabs becomes a horizontal tube. This guy comes here. Since it's sticky and extremal, we could apply the whole argument again to this set. And what do we know? That so we call those. So previously it was a slab S. So let's call it it's L, because now it looks like a horizontal tube, like neighborhood of a line. And then we apply the same argument. We know the following. If we look at the maybe I will just erase some part to make the picture cleaner. So now this is a set of is a sticky and extremal set of row tubes. If we apply the same argument with these row tubes, we know that locally inside a row to the 1/2 ball, this is going to be a union of those slabs of side length row to the 1/2 and thickness row. Because we are applying with the same argument, and then it's also parallel. Okay. So, and starting from here, we are going to find some product structure, but maybe before moving to those slabs, let me first say that the union of let me ignore the shading from now on. And then the union of those row tubes, let's call it the set E, can be parameterized as follows. X plus Fz times Y, YZ. So Y and Z, they are in 0, 1, and X is in AZ. So why can we parameterize as follows? Is because what this says is that this E is a union of parallel horizontal tube, and each horizontal tube, let's say fixed Z, a horizontal tube is just like a line segment. That's the direction is given by some number depending only on Z, because they are all parallel. So I will just give the slope a name called Fz. Because this is the slope of horizontal tubes at height Z. Okay. So that is why we could parameterize our sticky extremal Kakeya set as follows. Yeah. Are there any questions? Yes, that's a good question. So this is the Z direction, and let me just say that this is X. Is it? Yes, this direction is X, and then this direction is Y.
So what is AZ again?
Yes, that's a good question. So because this on each horizontal slice, this is the union of parallel horizontal tubes. The AZ will just denote the location of those. So yeah, that's a very good question, because our goal is, as you can see, the dimension of AZ is going to be the dimension of a Kakeya set minus 2. So our goal is to show that that this dimension should be 1. Okay. Now we can go to those yellow slabs. So what are we going to do is let me just okay. Let's just reparameterize such that the horizontal tubes at height 0, they are like in y direction. And what are we going to do is follows. So this is rho, and this direction has length 1. We are going to take we're going to take rho to the 1/2 neighborhood of one horizontal tube. So this has length 1. And since those red horizontal tubes are all part of the Kakeya set, so each of those balls inside this rho to the 1/2 square root of rho horizontal fat tube is going to be one of those balls that we could have that's going to be a union of slabs. I don't know if this picture becomes too messy. Let me for the first ball, let me parameterize such that the slabs point in the vertical direction, in this direction of z and y. So let's give them the name. This is L, and this is the yellow S. So L and S, they have to be. So this is from that picture applied to our new set, our new sticky set of tubes. We know that S has to be parallel with respect to L in this sense. They have to be aligned, because if they are not aligned, then our argument says that at each point you have an S. So if they are not aligned, let's say this S goes this way, then you know that at every point of L there is some S. So this will give us again locally a 3-dimensional set. So that is why. So those S, we call them local grains. And this L is called the global grains. And they have to be aligned. And we are going to, and not only they have to be, so they have to be aligned not just for the global grains at height 0, also at all other heights that intersected it. So, for example, I'm out of color, but let's say there are some other height of global grains here. They also have to be aligned with S. Perhaps it's more clear if I rescale this picture. So what I'm going to do is, this is a rho to 1/2 square root of rho. Okay. This fat tube, I'm going to rescale it to 1 times 1 times 1. And now later the picture will become more clear. So now after rescaling, those yellow S, those local grains, are going to be some tubes. And what's the radius here? This has size rho to the 1/2. Yeah, this is 1, and this is 1. So everything is 1. So now I can draw more pictures. and this is a consequence of S and L being aligned. So now you don't really see S being a slab, because then after rescaling, this is some row to the 1/2 tube that pointing up. And then at a different height, let me just slice this cube. Let's make it taller. At this height, we have another class of parallel tubes. Let me draw it this way. And at different y slice, yeah, maybe I should use slides. Then I have some pre-drawn picture. It's kind of hard to draw the picture on the blackboard. And the point is that this is some y equals to, let's say, y0, something like that. And there will be, suppose all the horizontal tubes intersecting this white, let's say this sigma y is the two plane whose y like parallel to the, so this is parallel to the xz plane, and the y coordinate is y. Then suppose it intersects at those points, then there will be some yellow tube going down. So maybe I should draw another. Yeah. I think for people who works in dynamics, this picture is kind of it's not so surprising. Basically, we have two family of vectors. Like one goes horizontally, and then the other one goes in the direction in the plane that parallel to the xz plane. And then we are going to sort of study the commutator of those vector fields. So, and this is the relation between local grains and global grains that eventually will give us some product structure that we are going to use projection theory to study it. Maybe I should pause and ask if there is any question with this picture. So this direction is given by fz10, and this yellow direction, let me give it some name. This yellow direction is given by let's say gy01, because again, after rescaling, each of those cube becomes those sigma y, the two plane that's parallel to xz plane, and the corresponding local grains becomes some tubes that's contained in this plane, and they are all parallel, so we might as well give them some slope, only depending on the two plane, the coordinate of the two plane. So this is the slope of those yellow grain, and we want to calculate how they commute. So here is what's going to happen. So this is okay, let me first say, let's say this is 0, 0, 0. And then we go to, let's say we go to this height. This is the height is z1, and we get this point is 0, 0, z1. Then we have a goes here, and then we travel along this red horizontal grain. This point is going to be fz. In fact, this should be a rescaling of fz. Let me just call this f tilde z. So f tilde z 1 y y z1. That's the coordinate of this point. And then we go down here. This point, the coordinate of this point becomes f tilde z1 y minus gy z1 minus, let's say this height is z2, z1 minus z2, and then y z2. And eventually we'll go to this point. And this is, the coordinate of this point is just f tilde z1 minus f tilde z2 y minus gy z1 minus z2. And then this is 0 and z2. But it doesn't, since we said that let's do the change of variable to make the first so to make the how to say the sigma 0, all the red the yellow tubes on this sigma 0 are vertical, so eventually this goes down, and this point is just the same thing with z2 equals to 0. So the point is that this thing is inside A0. Let's call A, give it a name. A is a rescaling of A0. So we have the following sum product structure. That is, if we let f to be f tilde z, so this is so here I use this quotation inside the 0-1 interval. It's just to say that well, technically it's not the entire 0-1 interval. It's some significant subset of the 0-1 interval. And then let's take g to be y minus gy and y in, again, 0-1 interval. Then we have the following: a plus f minus f dot product with g is again containing a. Why this is the case? Because I didn't draw the. Let's say this is the ground. That's 0, 0, 0. I didn't draw the corresponding horizontal tubes because otherwise it's too messy. But we start with our points A here. We start with a point A, then we travel. We'll calculate the corresponding commutator, and then we go down. This will again be in A. So that is where we have this sum product structure here. So this one is just that. Okay. And the goal is to use projection theory to study this sum product type structure. So at this stage, you might think that we have achieved a lot. So we have retrieved this very rigid structure, this sum product structure that we are going to analyze. And also, like, remember, A is a subset of the unit interval, and we want to show the dimension of A to be large. But unfortunately, at this stage, we have not yet distinguished the Kakeya set and the Heisenberg group, meaning that the Heisenberg group example has exactly the same structure. So we are going to need to use some projection theory to distinguish them. I will write what is the corresponding A and F and G for the Heisenberg group. So maybe first of all, do people understand what that notation means? A plus F minus A dot with G in A? I can write. So A is in 0, 1 interval. A plus F minus F. This is just A plus F. It's exactly the same, fz1 minus f tilde z2. Y, I should say comma, z1 minus z2. Dot product with y minus gy. This is that A is still containing A. For any z1, z2 in 0, 1, and y in 0, 1. And for any, also for any A in A. Okay, good. So that's the meaning of this sum product. Now let's talk about the bad news. Is that what is the corresponding one for the Heisenberg group? C case. So for the Heisenberg group, we can take G equals to and F equals to CC. So let's see. Oh, sorry. Y is here. Y bar. Then this is just R, which is like half-dimensional subfield of C. So it's not good because this will correspond to the case where dimension of A equals to 1/2 of the dimension of C, and this is corresponds to Wolff's 5/2 bound. So what we are going to use next is some projection theory to rule out this example. This is just one bad case, and there is another bad case also in R, but it's not so bad after all because it has a very rigid structure. So let's just look at this sum product, and can you imagine a scenario where this is exactly A? The scenario is the follows. So F is contained. Let's say F is this line, and then G is in the plane. G is the line that's perpendicular to F. Then F minus F dot with G is just a point then it's very easy to construct examples A plus a point is still in A. And I should say that all this is in a typical sense. It's not like we are not taking all of A. Maybe take like 10% of A and then 10% of something. Okay, so we are going to use projection theory to show that in R, this cannot happen. This could happen, but again, this gives us a very strong structure of F and G, and then we could conclude with some other projection theory, some other method. So the second step is sometimes we call it increase of regularity. The reason is that previously, I think I erased the formula for E. So previously, our union of tubes E is of the form x plus fz y and yz yz in unit interval and then x is in AZ. So previously, this is our like a parametrization of an extremal Kakeya set. The issue that we run into is that we don't really have a good information about Fz. Fz is just we give it a name to say that it's the slope at height z. Using induction on scales, meaning that if you apply our argument for all the rows, we could show that F is almost the Lipschitz. What it means is that the slopes at a certain height, so let's say at height 0, should be relatively close to the slope at height let's say rho, for some rho. Let's give another name for some r. What this means that, yeah, it's just Lipschitz means that fz1 minus fz2 is roughly less than z1 minus z2 for a typical pair of z1 and z2. And this is what we know. But suppose we have successfully reduced to the second case, then we could show that this roughly says that F is C2. And I will try to explain why it's the case. But this second case just says that we have we increase the regularity from Lipschitz to C2, and here we could do some other things. So let me first, so to reduce to this case, we use radial projections. And I will try to analyze that. Yeah, so we don't really need this picture anymore. Once we have this sum product structure, we could forget about the picture. So how do we use projection theory to analyze? First, we analyze this F minus F dot product with G. So let's do it step by step. Let's take theta inside F minus F. Then what is theta dot product with G? It's just an orthogonal projection because G is a subset. Is a subset in R2, and then let's say this is the direction theta, then these are the different color. So this is the theta dot product with G. I usually give it a name. Let's say pi theta is the orthogonal projection then we have the following Kaufman's projection theorem, Mastron-Kaufman's projection theorem. Says that so Mastron's projection theorem says for almost every theta in S1, and G is a subset of R2 or L, then pi theta G has dimension equals to the minimum of the dimension of G and 1. So Kaufman's projection theorem says that if we have a set lambda and lambda dimension lambda equals to 1, and sorry, this should read as, maybe I should have said, and G is 2 bar L, then for almost every theta in lambda. So suppose F minus F determines a one-dimensional set of directions, which is our lambda. Then we know that for almost every theta, this theta dot with G has dimension equals to the, so G has dimension 1. And then this has dimension equals to 1. And we are done because this is in A. So this shows that A has dimension 1. And again, we know that the whole goal is to show that A has dimension 1 because dimension of Kakeya set minus 2 equals to 1. Okay. So we are happy if F so we are good. So it suffices to show F minus F has dimension, determines a one-dimensional set of directions. Contains a one-dimensional set of directions. And so to study this topic, you should study the radial projection. So radial projection. So given x in R2, this pi x maps a point in R2 to a direction. So y maps to the direction between x and y. So here is our theorem. This is we show that if F is not contained in any line. So first of all, if F is contained in a line, then F minus F will just determine the direction of this line. So it just gives you one direction. So we need F not contained in any line. Then there exists X in F such that the dimension of pi X F equals to the minimum of dimension of F and 1. So this is our radial projection theorem. as you can see that this is what this says is suppose 2 does not happen. So if f is contained in a line, then it's quite easy to it's not hard to say that G has to be contained in a line perpendicular to f. So that reduces to case 2. But if f is not contained in any line, then we show that there exists, since f also has dimension 1, there exists a one-dimensional set of directions, and together with Marstrom's projection theorem, we are done. So that's how we use projection theorem. I should say that it's this theorem, we use this Bourgain's projection theorem, or Bourgain's discrete sum product, and it is precisely this theorem that distinguishes this. So let's say rules out C case. Why? Because let's look at the example. For that f, we can show that for that f, when f is C, then for any, then f minus f determines, has one real dimensional set of directions. And it's not contained in any complex line. So not contained in any C line, because this is complex conjugate. And it has a real dimensional set of directions, so it does not satisfy this bound. Let me just say, let me see. Yeah, let me just use the last 5 minutes or so to say how to conclude when f has more regularity. Are there any questions?
So, sorry, in your last theorem, the assumption on f is any subset of R2?
Yes, a Borel subset. Yeah. So, yeah, that's a good. So for, let's say let f be a Borel subset. This radial projection theorem has been generalized by Kevin Ren to all dimensions. So it's.
In higher dimensions, what's the condition?
That's a great question. In higher dimensions, this reduction is, you could still do it, but then what's going on is that, for example, in R4, your A now the difficult case is when A is not in the unit line segment, but A is in R2. So everything here has to, and so this dot product will become a little messy. So in R4, f is going to be, let's say, f1z, f2z, z, and g is going to be, so this y, g1, y, g2, y. So it's, no, sorry, let me try to figure out, so this y1, y2, g, y1, y2. So the difficult case is because in R4, we are still interested in the case when the slabs are 2 dimensions. So I erased the picture, but everything has to increase one dimension in some places, and it's no longer a radial projection. It's some other more complicated projection problem. One should probably need to use more structure than just two commutators, like the calculating the commutator between two vector fields. Yeah. Okay. So finally, let me use now recall that where is the formula for E? E is over there. To study the case 2. So let me just rewrite E now. Now here I say that f is roughly C2. Why this is the case? The reason is that the function, the graph capital F is like this F tilde is like some, let's say this is capital. A rescaling of this part is capital F, so that's rho to the 1/2. And we know that this is the graph F C Z. We know that locally it's contained in the, so here I say line, but since everything is discretized, it means that locally it's contained in some tube, like rectangular box. This has a width rho and length z. And so if we apply the same argument at all scales, it says that this curve can previously is just almost Lipschitz curve, and this can be covered by those rectangular boxes with length rho to the 1/2 and width rho. And if we apply this at many scales, at larger scale, it's also, let's say this is tau to the 1/2 and tau, or maybe say r. So using those many covered by many box structure, we can approximate it. We can say that f is approximately a C2 function. Like Lipschitz could go this way, but C2 has to go this way. So that is where this rectangular, like containing a line implies C2. And once this is C2, we could use some. So I should say that at this point we have distinguished real numbers and complex numbers, and we could forget about the issue of Heisenberg group after the application of the radial projection. So now we study another type of projection. We call it a twisted projection. This pi f maps E to R. So the map, I write it, so it's just x plus fz y z is maps to the x, which is contained in a z. So if I want to rewrite it, so let me use a capital X, capital Y, capital Z is mapped to capital X minus F capital Z Y. So this is the twisted projection. So pi F X Y Z is mapped to X minus F Z Y. Why this is useful? Because E contains lines, at least contains a significant part of lines of the form L, A, B, C, D is A, B, 0 plus C, D, 1, Z And what are we going to do is we fix B. We define the following projection PZ from R3 to R that maps CD to this A to pi f of A plus CZ, B plus DZ. See, this just means that we fix some number B, and this is pi f of this line, and we can rewrite it as A plus CZ minus FZ B plus DZ. I hope at this stage it's clear what theorem are we proving, so I'm going to erase it. And let's continue this PZ ACD. We can just rewrite it. Since we know what pi f is, it is equals to ACD dot product with 1Z minus FZ times Z. Then translate by FZB. So since B is fixed for each given Z, this is just a fixed number. So this is really an orthogonal projection in R3. This is a direction in R3. So let's call this theta, or maybe not theta, but this is a direction, and this PZ is an orthogonal projection. And so as Z moves from in the unit interval, this direction moves on the unit sphere. And let's say this is the direction. It is, since f is a C2, this direction is a C2 curve away from a great circle. So I didn't prove it be away from great circle, but this roughly corresponds to f prime z for some z. If f prime z is small for any z, then we could rule out by the Wolf axioms, because if f prime z is very small, then we can say that the picture is like roughly all going in the same direction. This does not hold for the Wolf axiom. So I'm going to ignore this, but let's say this is a C2 curve away from great circle, then so since we have Mastrom's projection theorem here, this Mastrom's projection theorem also holds in R3, but it reads as follows. For almost every direction in the unit sphere, the projection image has the correct dimension. But this is stronger because, so this is a theorem by Pramanik, Yang and Zahl, and also by Gan, Guth, and Maladag. They show that for almost every z, the Hausdorff dimension of Pz of I'm out of number. Let's call it J. Equals to the minimum of the Hausdorff dimension of J and 1. And so this is for J is a subset of R3. The assumption is that this PZ is the orthogonal projection with directions in a C2 curve that's away from any great circle. So what is J here? J is the set of, so we have the collection of A, B, C, D, where L, A, B, C, D is in the Kakeya set. So since this is a sticky Kakeya and this is that, forgetting B. So we forget about, let's take this to be J tilde, and J is J tilde forgetting B. Sorry, not forgetting, but fix B. Fix. Since this is a sticky Kakeya set, it contains, and also the number of tubes is like two-dimensional. So this dimension of J tilde is 2. And so for a typical B, by Fubini, for a typical B, the dimension of J is 1. And then we apply this restrictive projection theorem. It tells us that this has dimension 1. But what is this number, this PZ of J? It is, we know that PZ of J is contained in AZ because pi f of E is contained in AZ. And that's how we showed that dimension of AZ is 1, and we are done. Okay, so sorry for keep talking for a long time, but that was a good place to stop. Okay, and pause, I should say. Okay, so now we are going to talk about sticky to non-sticky case to general. So as we said previously, this is going to be used in the general case as well. But now let's okay, maybe first say that so this is a toy model, not okay. Some case. Let's say the number of tubes is roughly delta to the minus 2 and not sticky. So this implies that there exists some rho such that the number of rho tubes is much greater than rho to the minus 2. In this particular case, now let's examine the previous argument and see how it works for the, like what goes wrong for the non-sticky case. So we still have this decomposition. And here this is still true, but this is not true anymore because T rho is too many to be to satisfy the Kastar-Wolff axioms. So this is big. In an extremal example, for like let's say a toy case, we can take rho to be delta to the 1/2, and then we can take T rho to be let's say rho to the minus 4, and T is still delta to the minus 2. The picture is just inside each delta to the 1/2 tube. We take one delta tube and then some other delta tube. And this is a very non-sticky because the row tube has the maximum cardinality. In this case, the multiplicity of T row has to be row to the -2 because this is so big. So recall that this is roughly the union of T row. Since everything is contained in the unit ball, so this is at most 1, and this number is greater than row to the -2, because the number of row tubes is row to the -4. The volume of one row tube is row square. So this multiplicity is row to the -2. And this is very bad here because if we use the second bound, then this multiplicity becomes so huge that even if this is 1, it's not a very good estimate. So that is the difficulty for the general case. To study the general case, we should use the first approximate equality, the first decomposition. So recall that what this first decomposition means is that the multiplicity, the number of tubes passing through a point, is roughly the number of tubes passing through inside the row tube passing through this point, those tubes, times the multiplicity of grains. So here there are 2 grains passing through this point. This is because the thin tubes inside the row tube, if they intersect, they stay intersecting for a while, and this becomes grain. So those thin tubes intersecting this point, they intersect into a grain. So that's why we can do this decomposition. But the difficulty is that those grains, they do not have any structure. So here, even though this T row is like very big, but we could still imagine some sort of structure because T row is just thickening of the previous tubes. But these grains, they come from the intersection. We don't have a good control about the structure. So that is the main difficulty of studying the general case. The second decomposition is too lossy because usually this is big, but the first decomposition we don't know how to deal with the grains. So what are the grains? This delta times delta over row tube. So like the grains, since it has a length on delta over row, and radius delta, if we rescale it, it just becomes a set of row tubes. So the grains after rescaling, since we are only interested in the grains in the intersection of grains inside the delta over row ball because they have length delta over row. And after rescaling, they become a set of row tubes. So G is like approximately a set of row tubes. And that is why it's very reasonable to compare the multiplicity of grains and the multiplicity of T row because they have the same dimensions, they have the same radius. And like we know some information about that, but it's not usually a good news because sometimes this can be very big. We know nothing about the grains, and that for the hour left today, we are going to study a general factoring proposition to tell us how to find structure from an arbitrary set of row tubes or an arbitrary set of like let's say rectangular boxes. So that's the main topic of the day. I think this is probably one of the most important insight or idea in this reduction is how to find structure from an arbitrary set. and the proof is by pigeonholing, and we are going to do it very carefully. So it's self-contained, and we can and also important. So factoring proposition. I'm going to do it more generally because later we will also need to, when we do this argument, we will also need to factor a set of rectangular boxes. So I'm going to do it for general convex set. Suppose our blackboard V is a finite set of convex sets of approximately the same dimensions. In Rn. So what I mean is that, let's say the convex sets are V1 times V2 times Vn boxes. And so yes, so this is our assumption. So it's very general. Then how do we find any structure from it, and what kind of structure are we going to find? Then there exists a subset of V, a blackboard V, such that so this notation means that A is greater equal than log delta to the minus C to the minus B constant times the quantity V. Okay, so that's that's a good point. So usually delta just means the smallest scale. Let's say V1. So also as I write this, V1 is smaller than V2 is smaller than Vn. So let's say V1 is delta. What it really means is just subpolynomial powers of the smallest parameter. So it usually means that it's harmless to pretend this is greater or equal. And a set of convex sets. So a set blackboard W of convex sets of approximately the same dimensions. So that the following holds. One means this V, the set of V prime contained in W is roughly the same as W varies in our collection. So W is a convex set, is contained in the blackboard W. And second, each V is contained in roughly one many, so constant many W's. And third, this is how much we can do just by pigeonholing. So for any W in the collection, the density of V prime contained in W is roughly the maximal density of V prime. So what this means is that suppose this blackboard V prime, the subset, has large density, then W are the sets that sort of maximizes its density. And four. So let me just recall what this density means. And the maximal density is just the fourth says that for any the Frostman constant of V prime W in W is less than 1. So Frostman constant is defined as for any W prime in the this definition of this Frostman constant. And then number 5 is the maximal density of W is less than 1. So notice that this 3, 4, 5 essentially says the same thing. And 1 and 2 just says that everything is pretty nice. And it's like the 1 says this is almost a partition, and 2 says this is almost a partition, and 1 says that and each partition, this partition is quite uniform. Okay, so we call W maximum density factoring of V.
It's like a Bezikovich theorem?
Sorry?
It's like Bezikovich
Bezikovich theorem.
Covering
A bit
or Vitali or whatever.
You can see that the proof is by pigeonholing many times, yeah, I think it's just like some kind of covering theorem. So the assumption is very general, and the cost is that we have to pass to a significant subset of V. And as before, when we talk about this multiplicity, like refinements of multiplicity, so it is completely okay to pass to a significant subset or pass to like one refinement of the shading. So that's why when we apply it, we just go automatically to the subset without even mentioning it. So I think this is a very important proposition that's we are going to apply it again and again in the proof. Before I talk about the proof of this proposition, are there any questions about the statement? Yes?
Is the set hold W convex sets? Is this a disjoint convex set?
No.
So then if all of the convex sets in both W are the same?
Of roughly the same dimensions. Oh, you mean if they are all the same?
Yeah, if they're all the same.
No, but we have this maximal density bounded by 1. They cannot all be the same one, otherwise the density is big.
Oh, there exists. Sorry, I thought W was part of the state. Okay, there exists W.
Yes. Are there any other questions?
Draw a picture.
Yeah, sure. Well, this picture just says that if we have a any subset of I'm drawing V to be tubes because then for this picture we can just take W to be this box and then another box. Maybe it's more helpful if I give some examples. Okay, let's try to apply this theorem to several examples that we know. So first example, if the Katz-Tau constant, if the maximal density or the Katz-Tau constant of V is already less than 1, then what do we have when we apply this proposition? Then this proposition gives W equals to V. Right. And then another thing is if the Frostman constant of V in B1 is less than 1, and also those convex sets are, let's say, contained in B1, then what do we do when we apply this proposition? Then this gives us W is just the set of this one unit ball, and also V prime equals to V. Yeah. So that's the two examples to keep in mind. So recall that these are the assumptions for when V is a set of tubes. Those are the assumptions for our main theorem. So in fact, if we combine this factoring proposition with the main theorem, where there are two parts, one is how to estimate the union of tubes if the tubes are satisfy the Katz-Tau, or if the set of tubes is Frostman, then combined with this factoring proposition, our main theorem in fact says something about the union of tubes for an arbitrary set of tubes, because we could apply this proposition to find the corresponding structure, and then apply our theorem with respect to both W and V. Okay. Are there more questions?
Yes. So, in theorem 1 yesterday, in the assumption you had that the maximal, you had the Katz-Tau assumption, so it's kind of, you have this
Yes.
delta max at most 1.
Yeah.
So why do you need such a factoring proposition if you only care about
Yeah, that's what I mean here. So when we want to apply induction, and we want to bound the multiplicity, and to previously, the sticky case, we use this bound, but this bound becomes very bad if it's very non-sticky because the second term is huge. In the very non-sticky case, the number of T row could be very large, and the best we can do is it's not great. So we have to use the first decomposition. This is sharp almost sharp in after pigeonholing. So when we use the first decomposition, we want to understand the multiplicity of grains, and the grains that those red segments that coming from the tube intersections. So we have no control on the set of grains. We don't know anything about it. We know that after rescaling, it becomes a set of row tubes, and that's all we know. So that's why we need to apply factor proposition to the set of grains. So maybe I should say the idea is we are going to, for tomorrow, apply factoring proposition to the set of grains. But that is so the proof is via some greedy algorithm. So we have several steps. Step 1, we choose W0 to maximize this density and let V1 to be so what we are doing now is very simple. We just pick the, suppose the maximal density is much larger than 1, then we just pick the W0 or W0 to maximize its density, and then let V1 blackboard V1 to be the rest of the convex sets, and then we keep going. We choose W1 to maximize and then let V2 be V1. And we keep going until we stop. So until Vs is empty. Since it's a finite set of V's, so we are going to stop at some point. And so the second step is we are going to do some pigeonholing. And dimensions so dimensions means the side length of WJs. There exists J, which is a set of indices such that the following holds. This is greater than V, and what the set of indices for each J in J, Wj has okay, I should say that about same dimensions, and the density is also about the same for any J in a collection of indices, and then this has this is majority. Sorry, a significant subset. And the step 3 is the follows. Notice that if J is greater than K, then so this is just by the way we choose the WJs and by our definition. So set J1 be the first number in J. Let's give this a name. Let's call it this set. Let's call it V double prime, because later we are going to define V prime. Or maybe let me use triple prime. Okay. Since because it's a union of those Vj's, and each J is smaller or equal than J1. So we have that. We have the following. The maximal density. I know this becomes a little messy, but each step is not hard, but it's just there are many steps together. Okay, so what does this mean? The first inequality is just because V triple prime is a subset. And this is the definition of how we choose Wj1 to maximize the density in here. And this is because this is a subset of V triple prime. So that big, yeah. The last inequality is because this is included in V triple prime. So everything has to be equality. So here this has to be equality, and this has to be equality. And now we know that things have to be equality for J1. Now we are going to work with arbitrary J. In our collection, we know the follows. The maximal density of Vj1 is greater or equal than the which is roughly the same, and this is by pigeonholing. Which is as defined before. So this is the pigeonholing step. And again, we have like the same thing is like the same thing happens on two ends of the inequalities. So this means that this has to be roughly equal. Yeah, so we know the following. We know this, 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 the three things. In fact, all of them has to be roughly equal, but I just want to highlight the three quantities. Now, maybe before I keep going, what do I want to do is I want to show that I want to show V triple prime Wj is roughly the same as Vj Wj. This is not at the beginning. This is not obvious. The reason is that V triple prime might contain other objects that in Wj. Because the definition of those things, we keep deleting, but since V triple prime contains some of the earlier VJs, so it might contain some V that's in WJ. Might contain some, let's say V J minus 1 that's not contained here but contained here. So the goal this step is to show that this holds, and to do so we are going to see is via those train of inequalities that will eventually becomes almost equality. So how do we show this part? Maybe let me first ask. So this is our goal. Do people understand that this is not immediate because this set could be a lot larger? But we are going to make this happen by pigeonholing. Okay. So how do we do it? I think already from this reverse inequality we should have it. The reason is the follows. So this density is less than this density, so this guy is less than the maximal density because Wj is just some convex body. So that is less than maximum, but this maximum is approximately this one. So we have it's less or equal. But on the other hand, since triple prime contains that, it should always also be greater or equal. So I should. So this comes from this sequence of almost inequalities, and then the other way is just because of inclusion. So in the end, this curve gives approximately the same. And by the definition of the density, this just, and since we have that, since Wj has approximately same dimensions, since this is roughly the same. Yeah. So. Yeah. So that's it. That's the third step, and we are still going to have 3 steps. Yeah, I know there are a lot of inequalities, but before I move on, are there any questions?
So for this identity is for J in capital J.
Yes. Yeah. So from now on, at this point, we only care about capital J. Yeah. So step 4. So by step 3, we know that I'm just going to repeat. It's roughly then this triple prime is the disjoint union J in capital J. Then what do we know is that we can let V double prime be the set of V that is contained in roughly constant many W's. Then we have the reason is that V triple prime is the disjoint union of them, and since each is roughly the same as V triple prime Wj, so roughly speaking, they do not each V do not contain in too many Wj's. Otherwise, otherwise this is not true. So this is how we obtain the second. So this was how we obtain the second conclusion. And step 5. So since now we have deleted some of the V prime, some of the V's put in the V double prime, we want to do another pigeonholing. So there exists such that for any W inside, and the cardinality is roughly J. Yeah, so the number 5 is a consequence of this, because previously each of the V triple prime, this cardinality is about the same for each W, and we have deleted some of the V's, but not too many, so we still have this remaining. So this means that after there still should exist a significant subset, such that we have like preserved about the same number of V's. So for 5 we just use this, and now now finally we can give it a name. So V prime is just the union of V double primes, and W is contained in our set. So this is where we obtain our W's, blackboard W and V. Yeah, so, okay. And we're almost done. So this after all these long steps, just to show that 1 and 2 says that it's almost a partitioning, and it's almost a quite uniform partitioning. And from step 6, we're going to show that maybe before I talk about step 6, since we know that by the definition of V prime, since V prime W is roughly the same as V triple prime W for any W inside blackboard W, we have the follows. The first inequality is trivial, and then the second bound is from here. And then this is roughly delta max of V triple prime, which is greater than delta max of V prime. Okay, so only thing that's, so the first part is by definition, and this is because this triple prime is includes V prime. So this blackboard V prime is a subset of that, so this is also easy. And this is by our previous, by step 3, so by those long trains of inequalities, those are about the same. And this is by pigeonholing to such that they have approximately the same cardinality. So all I want to say is that now we could again conclude that all the inequalities are approximately equality. So this should be roughly the same. And this concludes our number 3. So this gives us item 3. Okay. And then, so now we have step 6. We are going to show the Frossman constant of V prime inside this is less than 1. Since we choose W to maximize the density so for any k, maybe let me not use the k. Let's say for any W star contained in Wj, we have the density of V prime W star is less than the density of Vj on W star. So I can also not write the included here, that they mean the same thing. Then this is less or equal than Vj W because of maximize. And this is roughly the same as V prime Wj. Okay. This is also from the sequence of inequalities in number 3. And so this concludes that the Frossman constant is bounded by 1. And finally, we prove step 7. So step 7, finally we show that the delta max of W's is less than 1. And how to do that, for any convex set U, the density of V in U, maybe let me still use this W star, just to not confuse myself, is equal to sum over V in V prime W star V. This is roughly V prime W. How are we going to do this? We split the sum into W inside. So we first sum on W and then sums the V's contained. And then I'm writing too big. So this is since all the cardinality are approximately the same, maybe let me write it this way. So delta V prime W star is approximately V prime W times V times W star times W divided by W star. Here I'm multiplying the volume of W's on both numerator and denominator. Then this quantity is delta V prime W, and this quantity is delta W star. We know that this is less or equal than 1. Let me see if this is true. No, not. Sorry, no, I'm confused. We know that this is less or equal than the density of V prime in W, because this guy maximizes the density. And so it means that this should be less than 1. And we are done. So this is since this is roughly the maximal density of V prime. Yeah, this is what we proved here. Okay, so that finished the proof of this factoring proposition. I know this is like, even though it's all pigeonholing, but there it's quite lengthy. Are there any questions?
Why do you use the fact that it's convex?
No, that's a good point. No, we didn't use anything about so this should hold in a larger generality. I didn't want to confuse people, but for example, in higher dimensions, one might need to do the same thing with semi-algebraic sets. But in R3, we only need to use convex sets. That's a very good comment. Are there any other questions? Okay, let me just, I have like maybe 10 minutes. Let me just say some consequence of this factoring. So, okay. So a consequence of this factoring proposition is that what we are going to do is we are going to apply the factoring proposition for the set of grains, which is, after rescaling, is a set of tubes. And then we are going to obtain some W's. The point is that we also need to understand the union of W's. So it's convenient. So we should so we need to understand. So this factoring proposition has decomposed into the W's and then also V's in W. So in order to understand the multiplicity of V, we will decompose into two terms. One is about the multiplicity of V inside W and also the multiplicity of W. And this is indeed can be done. So that's a factoring of shading. So suppose we have V and a shading on V. So this is why V is shading on V. Then there exist refinements like refinement y v prime of not exactly refinement, but I hope you like at least for the v's that we for the convex set that in v prime this is a refinement, and the shading on W, the set of W. So here, recall that the shading just means the union of balls, where the radius of the ball is corresponds to the smallest dimension of the convex set, the smallest side length of the convex set, such that the following holds. The multiplicity is bounded by So this is very similar to our previous multiplicity decomposition. And the second is just says that those preserves a significant fraction of the previous shading. So this is a prime. And this is again by pigeonholing, and since the factoring is almost a partition and is pretty uniform, so one could imagine after similar kind of pigeonholing, this is true. We have done the pigeonholing very carefully with the set of tubes, and when V is a set of tubes, and when W is a set of fat tubes. So similar things can be done here. that I'm not going to discuss in more details.
What is W? Is it the refinement?
That's the outcome of the factoring proposition. And V prime is the refinement. So yes, so what I'm discussing is that, so this is just about like convex sets. How do we find structure in that? How do we find the maximal density factoring? When we consider union of tubes, we should also consider those shading. And this is like slightly more technical. If you want to ignore shading, that's fine. But in order to make the proof rigorous, we need to consider shading. And this is how we deal with how shading behaves under factoring. So those V prime and W are the outcome of the factoring proposition. And now let me just write some. Previously, when we proved sticky Kakeya, we discussed the ideas in the proof of sticky Kakeya theorem. We have some inductive statement. So now I'm going to introduce two inductive statements for the general case, and then just definitions, but. And then tomorrow we'll prove the two main lemmas. Okay, it's going to be I don't know. Okay. So the statement is follows. So let k, kt, beta. So this first k means Kakeya, then this means Zahl beta, denote the following statement. So the quantifiers are always the same. So for any epsilon, for any eta, the following, so for any delta, the following holds. So the KKD beta is so let T be a set of delta tubes with maximal density less than delta to the minus eta, and the shading is delta to the eta dense. Then the multiplicity is bounded by delta to the minus epsilon, the number of tubes to the beta. So this is the statement k, kt, beta. And then Frostman beta statement is the same quantifier, and then let T be a set of delta tubes. That is, the Frostman constant is less than delta to the minus eta. Then for any dense delta to the eta dense shading, we have the following multiplicity bound. So this is less than delta to the minus epsilon, delta to the minus 2 beta, delta square, the number of tubes, to the 1 minus beta over 2. So those are the two inductive statements. And then let me just say we are going to the proof decompose into two main lemmas. The first one is so Zahl implies the Frostman version. So I should say that We will try to compare them later, but the second is assuming the self-improving. We have for some nu greater than 0. So those are the two main lemmas, and once we prove those two main lemmas, we conclude that beta should be 0. So now let's compare them. This is, if for those who, so this is in some sense similar to the Wolf's X-ray estimate, where he estimates a union of like, if we don't have one line in every direction, but we have like A lines in every direction, and then what's the dimension bound? But here, they are approximately the same if the number of tubes is roughly delta to the minus 2, because this term just becomes 1, and then they become approximately the same. They become the same. When the number of tubes is much greater than delta to the minus 2, one could also have an easy consequence of this by some randomizing argument to select a set. But this easy consequence will be weaker than this, the Frostman bound, because I should say that an easy consequence of the first estimate is going to be with 1 instead of beta to the over 2. And this is the improvement we get. This improvement roughly says that if we have a lot of tubes, we should expect more volume. That's the simple consequence. And here we choose beta over 2. I should say that the optimal, the natural one should be beta. But the reason we choose beta over 2 is because it will simplify one of the steps in the later proof. So anything positive means this part. Anything positive here would work. And the natural one is this, but we choose some beta over 2. And I think I will stop here.
Nu is uniform.
Sorry?
Nu is.
No, we don't need it to be uniform because we have this for any epsilon statement. So it's the same before the set of beta that it works is a closed set. So if we move it a little bit, then we can move it to the end. So this setup, although like we have this artificial epsilon here, allows us to not care too much about lower bound in the size of nu. It's just to make the statement cleaner, but in reality, we could trace how large nu is.
Okay.
Yes.
So you said that the convexity assumption in this proposition is not super important. You could replace it with semi-algebraicity. What would break down if you just assume that in this proof if it was semi-algebraic instead of convex?
You will see later, we will need to do some rescaling, and then it's much easier to rescale a rectangular box than rescale a semi-algebraic set.
But this proposition itself, will it hold?
Oh, this proposition, yes, it holds. It's just later in the proof.
Okay.
But how do you pigeonhole? Because for convex sets, it's clear you have logarithmically many scales, so it's easy to pigeonhole. But if you have to take into account a shape, how do you do this?
Usually, it's semi-algebraic set with bounded complexity. So. Yeah.
So we had already plenty of questions, so maybe it's a good time to stop. Thank you.
Thank you.